Presented by Caltech.
I'm David Tirrell. I'm the Provost here at Caltech and Professor of Chemistry and Chemical Engineering. I'd like to start by thanking all of you for coming and for your interest in the teaching and learning missions of Caltech. They're certainly central to what we do. These kinds of interactions are a source of great satisfaction, and they're certainly an important part of Caltech's impact on the world. We have 4 talks scheduled for the next hour or so. Claire Ralph is not feeling well today, and so Claire's not going to be with us, but we're going to hear from Evan Kirby, from Justin Bois, from Chiara Daraio, whom I haven't seen yet, and from Djorgovski. Sorry?
Santiago, Lombeyda.
Aha, okay, good. So we will hear from 5 people. Wonderful, thank you. All right. And so we will hear from them about methods that they're developing and evaluating in their own teaching. And I have to say, I'm really looking forward to hearing what they have to say. This is an extraordinary group of teachers and educators. And one thing that I do as provost, and I did when I was chair of chemistry and chemical engineering, is that I actually do try to understand how our students view the efforts of our faculty. And now, in a completely anonymous way, I'll just mention some of the things that's been said about this group, not identifying which individual got these comments, but I think they're representative of what effective teachers do. And they allow me to raise a point about the nature of the interaction between students and teachers that I think is important. So this is sort of typical of what I found. Goes above and beyond what is necessary, warm and welcoming, energetic, excited about the material, really loves teaching and cares about the students, gave captivating lectures and was passionate about the material, genuinely interested in student learning. The thing that I want to emphasize, there are 2 things that I want to emphasize there. When we think about teaching, when I think about teaching, oftentimes we wrestle with the question of how it is that we can explain concepts and help students understand concepts that they're encountering for the first time. And that's certainly an important role of a teacher. But in my personal opinion, it's not the most important role of a teacher. We're talking about subjects that demand a lifetime of study. And we're organizing 10-week courses. In my opinion, our most important role is to give students a reason to commit a lifetime of study to these subjects, because that's how they'll learn the subjects. And so there's a critically important motivational aspect. And I think some of the things that we're going to hear are ways of generating that motivation in the students in the classroom. And the second element that I think was very apparent in those comments is the human nature of the interaction. We're drawing people into the discipline. We want them to know that they're welcome in the discipline. And surely people enter our disciplines because of the intellectual engagement, but it's a very human activity. And it's a human activity for half a century for most of us. And we want them to see that early on and to embrace the human part of working in a scientific community. And so I think those are important messages that I'd like to leave with you from my own experience. I've been teaching for a little more than 40 years now, and I don't still quite understand what teachers do, but I have my own biases about what the role of a teacher is, and I've just told you what those biases are. The other thing that I would like to emphasize is that some of what we're going to hear about was fostered by the Innovation and Education Fund. That's a fund that Cindy Weinstein oversees out of the Provost's office. There'll be an announcement a little bit later in the spring. Typically, we request proposals, solicit proposals in April, and proposals for new educational innovations will typically be due about the 1st of July. And so I'd encourage all of you to think about ideas that you would like to explore, and if those ideas require some degree of financial support, we might be able to help in that regard. So I'm delighted that you're here. Thanks again to Cassandra and her staff for putting together not only today's event, but the events of the entire week. And we're going to start with Evan.
So thank you. I don't usually have the Provost introduce my Astronomy 101 lectures, but I don't really understand what's going on here. I sort of came in a little bit late, but this is Astronomy 101, the physics of stars, right? Yeah, okay, good. So today we're going to be learning about how the elements of the periodic table get created in stars in the universe. But we're not going to be looking at the periodic table. By the way, this is a really cool periodic table. But we're going to be looking instead at a different sort of space, which is called the table of nuclides. So instead of just the periodic table, which presents to you the number of protons in a nucleus, we're going to be looking at the number of neutrons on the x-axis and the number of protons on the y-axis. That number of protons corresponds to this periodic table. But now we have an additional dimension, which is which isotope are we looking at? And the important thing to note here is that the blue nuclides here are stable. They're not going to ever decay. But the other colors, the green, the red, and the yellow, those are unstable, and they're going to decay towards the blue colors. And one way that we can move around in this table of nuclides is the capture of neutrons. So one thing that's happening is that we have all of these neutrons flying around in some portions of the universe. So we can move from one nuclide, arsenic 75, to arsenic 76, by the capture of a neutron. So we're just adding a neutron and we're increasing the nuclide number by 1. Now if we have a whole bunch of neutrons flying around, we can do that 6 times and we can go from arsenic 75 all the way to arsenic 81. Or we could go to arsenic 82 if we have that many neutrons. So if we have a whole bunch of neutrons, we could very rapidly capture a whole bunch of neutrons to make really heavy nuclides of this element. Now these arsenic 81 is unstable, but you can tell it's unstable because it's not colored blue. And so the way that it decays, it's going to decay by what's called a beta decay. A beta particle is an electron or a positron. In this case, arsenic 81 is going to emit an electron and also an antineutrino, but we're not going to care about that today. It's going to emit this electron because it's going to take that extra neutron that it has and it's going to turn it into a proton. And the way that it does that is it emits an electron and this antineutrino. And so we can actually change the identity of the element from arsenic to selenium. Selenium has 1 more proton than arsenic. And so because we're turning this neutron into a proton, we have the same number of nucleons, which is the sum of the protons and the neutrons. So it's still 81, but we've changed the identity of the element. We could do it again. We can turn arsenic 81 to bromine 81 by the emission of another electron, the transmutation of another neutron to another proton. But we are not going to turn bromine 81 into krypton 81. Why is that? Because it's stable. Bromine 81 is stable. It's not going to decay. Excellent. Good. So you can see one possible way to move around in this table is if we have the capture of a neutron and then a decay, a beta decay. So we can turn arsenic 75 to arsenic 76. Arsenic 76 is unstable. We know that because it's not colored blue. And it's going to decay into selenium 76. Selenium 76 can then capture a neutron, selenium 77, 78, 79. Oh, selenium 79 is colored green. It's going to eventually decay into bromine 79. So if we have the very slow capture of neutrons, then every time we capture a neutron, there's not enough time for another neutron to be captured before it beta decays, if the number of neutrons is not very high. This is called the slow neutron capture process. But if we have a whole bunch of neutrons flying around, then we can have a rapid neutron capture process. And we can capture 6 neutrons here, or 7 neutrons, before we have that beta decay into this stable isotope, selenium-82. So we started off with arsenic 75, and very rapidly we captured 7 neutrons before we can finally beta decay into selenium-82. This is called the rapid neutron capture process. So you could see we could never make selenium-82 through the slow neutron capture process because we'd have to go through selenium-79 to selenium-80 and then through selenium-81, which is pretty unstable, to selenium-82. We never make that through the slow neutron capture process, but we could make it through the rapid neutron capture process where we have isotopes on this side of the table of nuclides beta decaying to the diagonal upper left. So it's activity time. I'd like to ask you to find someone that you like or don't like, I don't really care. Just find someone next to you, maybe in groups of 2 or 3, and answer this question for me. Which of the stable nuclides of krypton, which is this row in the table of nuclides, which of the blue-colored nuclides or isotopes of krypton can be made in the rapid neutron capture process? So get together with a partner and work it out. All right, in the interest of time, let me cut you short and let me get some answers. Does anybody have any ideas? Shout out an isotope. Krypton? 83. 83, that's a good one. I agree with you. Any other answers? I heard one over here. 86, that's the quintessential R process isotope of krypton. Because the only way to get there is through the beta decay this way. We can't really leapfrog all of these isotopes to get all the way up to krypton 86. Any other answers?
All of them.
No, not quite.
All of them can be made by the rapid process? I mean, I see 2 that could be made by the slow process.
Correct.
But couldn't they all be arrived at by the rapid process?
Explain.
Run it through the bottom row there, and then...
Look, let's say we start with germanium 82, it beta decays into arsenic 82, and then selenium 82. Krypton 82 is blocked by selenium 82.
No, what if you make bromine 82?
Bromine 82 would be made through the slow neutron capture process by capturing just 1 neutron onto... The fast neutron capture process, the definition is that we're going to neutron capture before it beta decays. So if we have the fast neutron capture process, bromine 81 is going to be way over here before it starts to beta decay.
What about 79?
79 is an unstable isotope. Bromine 79. Yes, indeed, you could make that through both process.
Capture and then beta decay to krypton 82.
Okay, now we're getting tricky. That's a very good point. Yes, 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 yes. So generally, the rapid process is you totally flood the bottom right side of the table of nuclides and then beta decay backwards. So we're really starting from way over here when we start to flood the neutrons and then populate this side of the table of nuclides. Okay, so I was going to ask you about the slow process, but in the interest of time, I'll just try to digest what I've just done here. So what I've just done is something called active learning. Active learning forces the students to talk to each other. And the reason for this is quite obvious. It just increases student engagement. If this was just some monolithic lecture, you might be bored by the time we got to this part in class. But instead, I made you stop and think about what you're actually doing and actually work out a problem. This is a very small change to a lecture environment style of a classroom. This is not an inverted classroom. It's not a huge change. It's a very small effort that you could do to increase student engagement. And the reason you might want to do that is because increased engagement translates to increased comprehension and increased learning. The principles of active learning is that I would suggest that you do very small, short activities, 4 minutes or less. If it takes longer than that, then it could start to get to be a different thing that I'm actually talking about. Then you're starting to get to a different style of teaching, which might be along the way to an inverted classroom. But if you want to just make small but very effective changes to your teaching, break up your lectures with little activities like this. Form groups, small groups. You don't want to have big groups where people can get distracted, but form small groups and make sure that everyone is talking to each other. I've noticed here at Caltech that sometimes these students, they like to work out the problems by themselves, but it's really important for the students to talk to each other. And then finally, ask for answers and discuss differences. So that's my suggestion to you. Thank you very much.
I bring a simple message. Share your course materials. Share them with your class, share them with the Caltech community, and share them with the world. Now, the most effective way to do this is by building websites for your classes or for your workshops. Now, ideally, the website is found by search engines and is persistent, which means that it remains even after your course is completed. Now, the benefits to doing this are many. So first, building a website encourages organization. I found that being forced to arrange materials in a navigable website has led to keeping my concepts and schedule more organized. Furthermore, the website serves as a consistent place where students, TAs, and even you and an instructor can go to sort of fetch the materials and to identify where the course is going. Now, it's important also for students who took your class in the past. I've had many students who have gone off to graduate study send me emails and say, hey, I look back at some previous course materials and they were really helpful for me in my graduate study. And importantly, posting materials on the web also allows other people at Caltech, students and faculty alike who are not taking your course, to know what the course entails. And this can really greatly assist in course design. You can know exactly what students are doing in prerequisite courses, and you can know exactly what's going to be required of them in later courses. But the sharing should go beyond Caltech. Like our research, our instructional materials are our intellectual product. We should share them, ideally with the same care and scope with which we share our research product. Now, building a website from scratch can be difficult, and making it persistent and searchable is even harder. But fortunately, you can kind of step your way there. Caltech IMSS offers use of Moodle, which is an integrated learning program that you can use to host a course. It enables posting of course materials, announcements, and also for some student interaction and discussion. Now, as I was discussing this talk with one of my colleagues, he made the following comment about Moodle. I quote, "The best part is that someone else takes care of everything. I know it could look prettier, but whatever." And I agree with him, and he has a beautiful Moodle site for his course. But it does speak to an issue, which is while it's great for getting you started sharing your materials with a low barrier of entry, it does have drawbacks that although it's modular and configurable, it is necessarily more restrictive than if you build a custom website. There are also some barriers to sharing Moodle pages globally. Although that is possible, I found that to be quite difficult, especially the way it's hosted with IMSS. You basically need to have a Caltech login to get into it, so the global sharing becomes more of a challenge. So generally speaking, I prefer to create custom web pages for my courses. And while it does require some basic HTML and CSS, I have found that you can make nicely formatted, navigable, static websites without having to do too much fancy web coding. Now finally, you should make your course content persistent. And to do that, you can obtain a digital object identifier, or DOI. You may be familiar with those for persistent links to research publications. And I'll talk more about those in a few moments. Now once you decide to make a web page and globally share your course materials, here are a few tips to help you do it. So first off, you should explicitly copyright all of your materials. In the absence of explicit copyright, one must assume a restrictive copyright. This is by law, and this can essentially make your materials unusable to anyone else who wants to use them. Just because it's on the internet doesn't mean that you get to use it how you please. So you need to explicitly have the copyright, and so I explicitly copyright it to me with, I use a CC BY4 license for any written materials and an MIT license for any code. And both of these are very permissive licenses, so the materials can be used how anybody pleases, provided they give attribution. Now you can host your website, so hosting is another consideration, and you can host your website with IMSS, but above a certain disk quota, you're going to have to pay for it. And for courses with lots of data, I use Amazon Web Services, or AWS, to host it. I just plot my course in an S3 bucket. If you don't know what that is, that's okay. It's basically just cloud storage that's accessible to the world. But I have found hosting on GitHub to be easiest, and it also has the benefit that allows students to easily clone the entirety of the course materials to their local machine, organize exactly how you want it organized, that they can do whatever they want with for the rest of their careers. Now, an issue with hosting on GitHub and with AWS, unless you want to pay to have a non-static hosting for the latter, is that you cannot password protect files, which I often want to do with things like homework solutions. So for that, I usually password protect files on IMSS, or sometimes using Dropbox, which allow pretty easy and cost-effective password protection. Okay, so the password protection gives a challenge to sharing your course materials. But there are other issues as well. For example, you may want to have some sort of discussion of your capabilities for discussion for your students in the course, and there are platforms to do that, like Piazza, CampusWire, or Moodle. I use Piazza, but the problem is that the discussion is separate from the content. Another issue is that we may also want to use some copyrighted content in our course materials, such as figures from papers. This can be a challenge as well because the guidelines for educational fair use are ambiguous, especially when things are shared on the web. Now, finally, I mentioned to you before that you should get a DOI to have your web content be persistent. Now, there are many logistical and technical issues with DOI assignment. I won't get into them, except to say that I'm currently working with our library staff to set this up for course materials for persistent DOIs, and they are experts on this and are working through what some of those challenges are. And they'll soon be prototyping some of my courses. So when you do get around to wanting to have a DOI for your course, you should check with our talented library staff. So now I'll just give you a couple examples of some websites for courses that I teach, my course on data analysis and my course on a boot camp that I do on programming. So this is a course on data analysis, and so this is just a web page that I designed, and it has a splash page. Notice at the bottom it has links to every previous edition of the course, so a student who took it before can go back and see what he or she did. I have a policies tab, which has the stuff that's commonly in a syllabus, which tells you about grading procedures, homework submission, when we meet, late policies, these sort of things. I have a schedule that says what we're doing when, like for every lab or tutorial, and recitation. And the other course I want to show you quickly is this boot camp, which has a schedule for what we did during the week. All of the lessons are there. For example, the lesson on for loops. I can click on it, notice the copyright with explicit permissions. And importantly, I can click on the Git repo, and I have all of the course content available that they can clone and keep on their own local machine. Thanks.
My advisor wasn't able to make it, so I will take care of the presentation for her. So essentially, in this presentation, what I would like to show you is an experiment that we've done in Chiara's class, and I was part of it. And essentially, these experiments boils down to coming up with a platform that students can relate to, and a platform that can be used for improve the students' knowledge, to make them understand really certain concepts that we teach in a theoretical fashion, and make them put this knowledge to practice. So the title of this presentation is Building an Understanding Brick by Brick, and essentially it's about using modular platforms for in-class experiments. So essentially, I would like to give you a brief introduction about the course that we have been teaching. This is a graduate course in civil engineering and applied mechanics, and it's related to structural dynamics and wave propagation. So it boils down to trying to understand, trying to teach students how waves propagate in solids. And this is a problem that it's extremely important for different fields. In civil engineering, for example, earthquakes manifest themselves as waves that propagate through soil, while in more mechanical engineering type of problems, like many mechanical components are affected by problems of vibrations. And understanding how to manage these vibrations is very important technologically, and we teach some fundamentals about this in the class. The class usually, historically, combines some classical wave mechanics, so some fundamentals, and some more research-oriented topics. And this is a bit the legacy of my advisor. That's what she introduced in the class a few years back. The class is typically small, 10 to 15 students. So it's a manageable group of students. And previously, it was only based on theoretical lectures. So everything about this started really when essentially I joined Chiara's group 1.5 years ago. And during my PhD, together with my advisor at the University of Minnesota, we developed a platform to test some very novel vibration concepts using Lego bricks. So this is something that we did back in 2015. And this is an example of, I will show you briefly what this is about. Essentially, we have some plates. You can see there is like a Lego plate with some bricks attached to it. This is a prototypical version of a metamaterial, what we call a metamaterial. That is a solid that is designed in order to have some enhanced wave manipulation capabilities. In this case, for example, by just placing these Lego bricks on the base plate, it is possible to introduce some interesting dynamics in the system. And you can see it over there in that plot. Basically, what the plot shows you, so let me explain a bit better. So we have this plate, and we are shaking it. So we're shaking the plate. We're sending some waves at different frequencies. And then we're recording the response outside, where the bricks are not present, and the response inside, where the bricks are present. And what the plot shows is essentially how the waves are transmitted through the medium. So how much energy actually goes into the region that is shielded by the bricks. And you can see that it's a plot of transmission versus frequency. At certain frequencies, you have wave attenuation. You can see these dips in the frequency response, which mean the waves for those specific frequencies cannot go inside the medium. And if you can see up there, there are some experimentally reconstructed plots of how the plate is actually moving. And you can see that at the frequencies that correspond to those bands, nothing propagates. So there is essentially this Lego platform is functioning as a shield. So this is a bit the platform that I came up with back then. And what we thought about with Chiara was this is a perfect platform. This is a platform that people can relate to because of the Lego component. And because also it's very modular, so you can play around. You can change the arrangement of the bricks, and you can see what happens to the different attenuation regimes. And therefore, we decided to try to implement this in air vibration and dynamics class. So basically, it allows to test many relevant wave manipulation effects. And the attributes of this platform are that it is modular, it's reconfigurable, and it's very intuitive. So how we implemented this, essentially we built a small-scale setup that is very similar to the one that I made back then at the University of Minnesota. And in this small-scale setup, everything is on a cart, essentially. And on this cart, we have specimens, which are the structures that we actually want to test. We shake them, and we measure the response with that device over there, which is a non-contact vibration device, vibration measurement device, that basically allows you to measure how the waves are propagating in the system in different points. And we have, within this cart, also some signal generation and data acquisition system. And essentially, our implementation so far has consisted of a couple of parts. First of all, we do 3 lectures in class, which are experimental lectures that feature 30 minutes demonstration led by the TA, in which we basically show a bit how the setup works. And then for the rest of the lecture, for the rest of the hour, essentially the students can do hands-on tests. So they actually go up to the platform, they come up with their own structure, and then they test them to see if indeed what they've learned in class can be put to the test in this way. So the 3 lectures that we basically are doing related to this are first, an explanation of the setup. Second, some tests on wave filtering, basic wave filtering, so like what I showed you in the previous slide. And then some tests on more complicated wave effects. But basically, this is in a nutshell, what were our goals and how we evaluated the students based on this. So the goal was essentially for the students to learn some basics about experimental wave mechanics, or experimental devices in general, and to really cement some of the notions that they have learned about in class using theoretical demonstration. And also to practice some typically research-related activities like literature searching, because in the end, everything boils down, the students are evaluated based on a final project, where we we ask them to find an interesting article on this, on wave propagation and these metamaterials, and then to plan an experiment based on this Lego platform, of course, related to the article that they have found, and then perform the experiments. And for performing the experiments, we allocate them a certain amount of time, more or less 5 hours per group, in which they can really work on it and do their mini research project. And this is, for example, some of the presentations, so the first slides of the presentations that the students did last year. And they have looked really, I was really amazed, working with them. It was so nice how they enjoyed this. You could really tell that they were proud of the article they found. They were proud of trying to figure out how to make it happen in real life. And overall, I think it was very satisfactory, both for us, teachers, and for them, students. Moving forward, we're actually repeating this activity right now. The first experimental lecture in our course is going to be in a couple of weeks. And we are trying to replace some of the equipment in order to allow for more complicated experiments. And also, at the same time, this platform is also very powerful when it comes to outreach. So not just for teaching in class. So we're actually using it. For example, we used it back then at the Caltech Science for March, where we had a demonstration of how essentially this platform can be used to show you that metamaterials can be used to insulate buildings from earthquakes. And we had the same Lego plate with the bricks underneath. We were basically shaking it on one side, and we were showing that for certain frequencies, that metamaterial basically shields a 3D printed building from incoming waves. So that's a bit what we've done, and yeah, thank you for your attention.
There you go. So my name is Santiago. And I'm going to be talking to you a little bit about our tool we created called Enhanced Reality for Teaching. It was partially funded by the Provost Innovation Education Fund, so thank you for that. And this was work that I did with Djorgovski, as well as 3 second-year students in computer science, Lucy, Netra, and Maya. And they did all of the development this last summer for their SURF program. So all the work that you see here today was implemented by them. So what is ERT? ERT is basically a collaborative virtual classroom. Now, what's interesting about it is these 3 things. First of all, it was implemented to actually work in virtual reality. So it actually means actually putting the goggles in and then jumping in there and feeling immersed and flying through the space. No flying, actually. The second thing is because we actually are in this immersive space, this allows us to create tools that are usually not available easily for an education environment. And the last part, which is the most exciting part, is that this gives us the capability to embed full simulations or labs or just ability to see models and actually interact with them and experience them firsthand. And that's probably the most exciting thing of all. So let's start from the first thing. So why virtual reality? So obviously, virtual reality has become a lot more available nowadays. You can spend $200 on a headset. The new modern computers can actually run full virtual reality from a laptop. But it allows us to actually experience life in a different way, right? It gives us new experiences, new abilities to understand ways. The other thing that allows is actually gives you access to things remotely, right? So a student can be at 2 o'clock in the morning putting this headset, actually doing their lab. And it also allows us to do things that otherwise would be prohibitively expensive, right? You couldn't have them, messing around with experimental things where it takes $10,000 to run an X10 machine every time, right? But you can do it in a virtual environment, and you can do it as many times as you want. And it also allows us to operate at all sorts of different scales, right? You could do nanoscale things, you could do astrophysical simulations, all within the same space. So what do I mean by space? So this is our virtual classroom. This is the top view. You start at this glass platform in the front, and then you start walking in. And the first thing that you see is you see desks for the students and a desk for the instructor at the end. We're trying to create a real environment, something that feels real. Part of it, for instance, we actually calibrate. So the moment you start this program, you calibrate with your front desk. So then even if you're wearing the goggles, if you feel forward, you actually feel your actual desk. And that really reduces the anxiety quite a bit, let me tell you. You feel like you're not going to bump into things. But then when you get to the desk, here's the teacher desk. Here on the right side, you have your slides. In the middle, you have your notes. On the left, you actually have a blackboard you can actually draw in, and it'll show up in the back. That versus the student desk, which looks fairly similar. We've debated whether to include, Facebook Messenger on the right. But we have buttons and other things, which I'll talk about in a little bit. Now notice that it's open, it's bright. You can see outside. Our brains are dumb at some things, so showing them bright lights and sunny sky actually keeps you awake. Having floor and be able to feel your chair and your table lets you actually work in this virtual environment for a couple hours without being too nauseous. I get nauseous very easily too. So. Now on the left side, you actually see at the end also these alcoves. So this is where people actually go and collaborate. You have the spaces where you can actually interact with a model together. You have a big blackboard that you can work in, and you can see each other and talk to each other. And the audio is isolated just to that small alcove. And of course, the ability to take notes, although right now it's pretty chunky and slow. Now, how do we come up with all these little different things? We actually used user experience methodologies. Netra, Maya, and Lucy actually went to their classrooms and took notes on what other students were doing. What were they finding obstacles with? Where were they getting kind of frustrated? What were the problems? And then we conducted interviews with students and instructors as well, as to see what were the obstacles, what are the problems. And from that, we were able to gather all different solutions that we could come up that were actually quite good to work in virtual reality. So the first thing to do is you do paper prototyping. You don't want to go in and start just programming like a maniac. You do actually paper things. We actually see how does this interact? How does this feel? Does this work or not? And then we actually implemented the solution. So just one sample thing, for instance, that we did is we're used to the clicker. We have A, B, C. The teacher asks, is it A, B, C, or D? But the other thing that we have, for instance, is two buttons. One is a question button, which is equivalent of just raising your hand. The other one is a confused button. So basically, if you're listening to something and you don't understand, you kind of just discreetly press your confused button, and anonymously it shows in the teacher's and instructor's desk. Now, it doesn't tell her who it is, but it keeps a count. So eventually, if they notice all of a sudden half of the class has no idea what you're talking about, she can go backwards and explain it. So that, for me, would be amazingly useful, because nobody understands what I'm saying ever. But these are the kind of tools that are available, and this actually came from Caltech students. A lot of them are shy to ask questions, so this would actually be a viable solution, especially here. Now, the last part to it is actually the ability to actually implement full simulations, full models within this space, and that's what we're mostly excited about. We've done some collaborations with oceanographers, lately with Andy Thompson. With biologists, we work with Matt Thompson, as well as Paul Sternberg. So the one in the middle is actually a view of the Sternberg worm from the middle, kind of looking at all the cells going downwards. And the left is actually a 3D scatter plot. And the whole idea of actually depth perception for all these models is until you see it, until you experience it, you don't realize how necessary it is. And not only that, but you can experience that in a 2D screen. But until you have it permanently next to you, it just distracts from your ability to understand. So here's a very small sample of the smoothed particle hydrodynamics model, SPH, on the alcove. Here's the same thing in the space, and here's the student, or as well as the desk. So these are all models that people can interact with. You can change the constants for attraction or repelling, and you can see how you could actually do either a fluid or you could do an astrophysics simulation, all using SPH. So where are we going with this? Well, we've done small tests with 3 people. We want to see how much we can scale it within just the free servers that we can operate in. We are conducting an actual workshop on SPH that Mathieu Desbrun is going to be doing. So we're actually trying to implement a full SPH model within this space. And really, there's tons of things we can measure about how effective education can actually be in virtual reality and how we can actually start deploying it at Caltech and other spaces. We encourage you to ask us for a demo. We love giving demos. If anybody has any questions, I'll be glad to answer them later on. Thank you.
So huge thanks to all of our speakers today. You will get a chance to ask them questions in just a moment. I am Cassandra Horii, Director of the Center for Teaching, Learning, and Outreach, but Claire really wanted to be here today, and I just want to acknowledge the great work that she and her colleagues in computing and mathematical science are doing. Hopefully we'll get Claire back to another event in the future to talk about CS 141, Hack Society, Projects for the Public Sector. This class is really about connecting our Caltech students to form and create some wonderful innovative solutions really for problems that are live and important in our society today. One thing that Claire and her colleagues have thought about doing and are starting to implement, which I think is really exciting, in working with public partners such as Miracle Messages, which is a nonprofit connecting those experiencing homelessness with their loved ones. Often they've been out of touch for many decades, so this is a platform that allows them to reconnect. So our Caltech students are building a whole new database and front end for that work, getting them out of free, simple kinds of shared documents and into something that will really work for them long term. But Caltech alumni are helping to advise and mentor these projects, which really makes this kind of community impact much more possible and allows our students to really make a difference. So let's give Claire a round of applause, and we'll have her back. So you will get to ask some questions. We're going to do a quick think, pair, share. Who knows what a think, pair, share is, thanks to Jen and the work of CTLO? Yes. All right, so about half of us know what this is. It's a pretty well-documented method across disciplines. I get to give you a little bit of a plug here. There are these wonderful sites with resources for different areas, different disciplines in the sciences. CERC focuses a little bit more on the geosciences, but has resources and methods across all of our disciplines. Physport is another one with great resources for teaching physics, astronomy, and related fields. And even the Mathematical Association of America has a pretty amazing guide for instructional practices. So think, pair, share shows up in all of these spaces, all of these places, because it just works and it's so easy to pick up. This kind of picks up on what Evan Kirby was talking about a little bit earlier as well. Here we go. So take a moment, talk with someone next to you. What's one idea from today that inspired you, and how might you adapt it for your classroom, your lab, your group, or other potential settings? I'm going to give you 2 minutes to talk. At the end, we'll hear a few, and you can ask a few questions of our speakers today as well. Ready, set, go. Super. So I'd love to hear from someone over on this side of the room. Thank you for not wanting to stop talking. What is one idea that you'd be willing to share for how you'd like to adapt or be inspired by one of these ideas? Jen has a mic and is going to bring it to someone on this side of the room. One idea? Yes, thank you.
I kind of like the idea of the confuse button, and I feel like there would maybe be ways of like implementing it into a classroom, even like with that before getting into virtual reality, just like to be able to gauge at what point students are getting lost without having to constantly be checking or look for confused looks.
Yeah, fantastic. So you might have a low-tech version of any of these things until we're all in the virtual. We'll be there soon. We'll all be there soon. How about another idea? Another adaptation, inspiration, something else that someone would like to share? Oh, was there someone in the back?
Well, we're from the safety office.
Yes.
We don't necessarily teach, but we train. And one of the aspects that we can't really train easily people on is the hands-on training. You know, work with hazardous chemicals and hazardous biological material. How do you learn hands-on on doing it safely? And so the appeal of a virtual space to start, you know, training on that is actually very, very appealing, because right now we don't have an hands-on lab, and it, you know, takes resources and space. And if we can not use a space but use a virtual space, that would be absolutely awesome.
Fantastic. We have another customer for virtual labs. How about one thought from over here toward this side of the room? One inspiration, something that you might try?
I guess we both thought like making a website is like kind of useful, and it helps us to be organized, and also helps us to be quite transparent in terms of how we write our lecture notes, homework. So it just helps overall in teaching and learning.
Fantastic. And I am excited, too, that that conversation has started the work on potentially having DOIs, permanent references for courses as well. So any questions for our presenters? Is there anything you'd like to find out more about from anyone who spoke today? Did you have a question? No? Yes, right there. Oh, here, there's a microphone. Yeah.
You mentioned nausea a lot when you were talking about the VR setup, and like that is an unanticipated problem. So I guess, are there other could you talk more about that, or like other unanticipated issues?
Sure, I'm the kind of person that kind of tends to get car sick unless I'm driving myself.
Same.
So I mean, a lot of it has to do with the refresh rate of the headset. If you have a pretty decent headset and the refresh rate is above 60 hertz for each eye, you're pretty good. But once your ground starts moving, which happens a lot if you actually have your avatar walk, or you actually use like a fly motion, then I get seasick really quick. And one way to avoid that is first of all to do things like teleportation, where you say, okay, rather from going from here, you just go to a lobby. Then from the lobby, you go smoothly to your seat. And that actually tones that down a lot. And then once you encourage the user to actually be in a sitting down position, And the moment you reach out and you feel for real objects, then you feel like a good sense of what's called presence. So if you have a good sense of presence, that just diminishes your ground motion sickness quite a bit. So there's definitely studies going in that direction. There's definitely ways to combat that. It's not the mainstream, because right now the mainstream is run around and shoot other people. Zombies. And zombies, sorry.
Thank you.
This one's for Justin mostly. I'm curious how you think about, in terms of reproducing and sharing your course in terms of like video recording it. Do you video record your courses? Have you thought about it? How do you think about that in the context of sharing like the whole course as a package?
I think I have a pretty unpopular opinion about video recording courses, which is that I don't really see that as much value to that. For example, I don't ever share slides. I rarely share slides, I should say, with students, because slides are meant for support for speaking. Lecture notes are meant for reading. And so I try to prepare documents that are for the type of activity that they're doing. So like for coding activities, it's definitely never slides, and it's not actually a PDF, it's an executable. I usually use Jupyter notebooks, but you can use Observable HQ, whatever. I mean, something executable. And so just in my own experience, I find I get, like whenever I try to watch a lecture on YouTube, I definitely have it on 1.5x, because and I can read so much faster. And so I generally don't record lectures. I don't know. I think that they're much better experienced in person. I'm just not a big fan of video lectures, so that's kind of a non-answer. I just don't like to do it. So yeah.
Yes.
Can I amend that? I've done 3 different MOOCs, and I find that they're really wonderful experience and great way to scale your sharing to the whole world, not just a few tens of people in your classroom. So I personally think that's an excellent addition to the whole arsenal of tools that we're using.
Thank you. One more question, yeah.
Yeah, just to bounce back on what you just said, it kind of feels like you're advising people against going to your lecture event, or because it's too slow.
I'm very funny. I tell a lot of jokes. Last year I did my first magic trick in lecture, so that went pretty well. No, but
you see the point I'm making, but actually a lot of undergrads choose not to go to the lectures. They would prefer to just read the lecture notes.
Exactly, and so for example, I'm working on converting all of my courses to this type of format, but for one of my courses it's pretty much completely converted. The students are expected to read ahead of time, and then I have sets of questions that they respond to, and they're due an hour before lecture, and GitHub is great. They just commit it, and then I look at all their commits and see what they did, and I can identify, and I don't lecture, I lecture, but my lecture is not written ahead of time. I specifically talk about what the problem areas are, where they got all the material from reading. And I try not to talk too much, and instead I hire excellent TAs, like some of them sitting in this room, and the students actually are working while we're there, and I try to spend more of the class time with more individualized instruction as opposed to orating.
So I'm super excited by the ways in which we see the kind of thinking and the depth of what students are capable of coming into the classroom, whether it's virtual or real. We hope you're leaving with a few new ideas and inspirations today. Thank you so much for coming.